lost thing, right? But I'm on that to keep me from killing y'all.
Well, that's not exactly the type of inhibition I was thinking about. We're talking more about inhibiting chemical reactions rather than inhibiting psychosis. But the principles are exactly the same. In a reaction where an inhibitor is involved, putting it in place actually slows things down. So we've talked a lot about accelerating reactions, but in the simple analogy of using your car, there's a gas pedal that speeds things up and there's a brake pedal that slows it down. You don't want to be applying both at once, so you need to know which one does what, and that's kind of how we have to look at certain reactions to figure out what is inhibitory and exactly at what order, because some things are extremely inhibitory. Like your parking brake. If you pull that while you're driving, it's much more of an aggressive stopping mechanism than slightly applying the regular brakes. So with that in mind, this is an example of a reaction that does have an inhibitor as part of it. As before, we need a lot of data because we need to actually isolate the orders for everything else. And at first, it's not going to be clear which one's the inhibitor, so we have a table of generally doubling of concentrations, and then we observe what happens to the rates. Sometimes we go double, triple, quadruple. We're still going to be looking at what happens to the rate and comparing it to solve for the reaction orders exactly the same way we did before. So you can look back at the, rate laws lecture to figure out how to do that. I'm not going to go through it again here. I want this to just be a little faster, no pun intended. So if we compare the first two trials, you can see that the iodide concentration is the only thing that changes. It doubles from 1.3 to times 10 to the third to 2.6 times 10 to the third. And we can start to eyeball what happens to the rate. 9.4, roughly half of 18.7, slightly off. So what we end up with here is a 2 to the x that's approximately 2. Now, since we know that this number has to be an integer or a half, it really doesn't have any other options, then we could actually work this out the long way, or we could just eyeball it and say that 2 to the x here is 2, so therefore x is 1. We can do a very similar procedure for the reaction order for the OCl minus ion. If you notice trials 1 and 3, that concentration has changed where the iodide concentration, the hydroxide concentrations have not, and the rate goes up. But in this case, they decided not to be nice to us by using nice even numbers in concentration change. The concentration here goes up by 50%, so 1.5-fold change, a 1.5 multiplier. And if we actually do the math, we end up with the two rate changes on the side here, 14 versus 9.4, is a 1.49 ratio. So we end up with 1.5 to the y equals 1.49. So okay, yet again, it's still a whole number. We can see that relatively easily. It's y equals 1. It's the last one that's a little on the weird side. So we're going to be looking here at trials 1 and 4. So if you look at it, the iodide concentration, 1.3 times 10 to the minus 3, has not changed. The OCl minus concentration, the hypochlorite concentration, 1.2 times 10 to the minus 2, has not changed. Here's the weird one. The concentration for the hydroxide, 0.10 up to 0.20, and look what happens to the rate. It goes down. It goes down from 9.4 times 10 to the minus 3 to 4.7. So when we do the math on this, we actually end up with 1/2, or 0.5, equals 2 to the z. So that's what an inhibitor actually looks like when you see it. Is you're adding more of it, but the rate slows down. Now that's not surprising in everyday life, but in terms of chemical reactions, that's a little abnormal. We don't see that a lot. In terms of pharmacokinetics, that's usually the goal. But in terms of strictly chemical reaction kinetics, that's not normally behavior that we see. Either something is not useful at all and has no effect on the rate, or it tends to speed things up if it's involved in the reaction. So in this case, we have 0.5 times 2 to the z. 0.5 equals 2 to the z. And so we can solve for z as minus 1. So this is a -1 order. So it's a direct concentration inhibitor. It's rare to see inhibitors that are more than negative first order, but you still need to check that to be certain. Don't just assume it. We don't like to make assumptions when it comes to rate. It's like assuming you can do 100 around a curve in your car. It's probably not a good assumption. It could get you in a lot of trouble. So with this, we can now actually put all the numbers in place as the exponents, and we can use any trial we want, as before, to solve for the rate constant. That's a relatively direct process, just putting in all the concentrations. The only problem that some people will have here is just keeping track of the order of operations. You don't want to lose any of the pieces when you're adding those exponents. So make sure that when you're multiplying these through, that with the hydroxide concentration, you end up dividing by it because it has a -1 exponent. All right, so you can do that, solve for K, and then we put that back in, and we now have, as before with the last lecture, the complete rate equation. It's going to give us the entire picture over a relatively small range of concentration changes, but we have to start with something, and this is a very good start. But it's an example of where a reaction is inhibited by adding more of a concentration of a reagent to it.